Welcome everyone to the AFFOA Member Spotlight webinar. This one is Galvorn, Driving the Multifunctional Revolution in Advanced Textiles with the company called DexMat. DexMat does some amazing things. I can't wait for everyone to be able to hear about what they're doing and in some of the applications. It's just Galvorn is pretty interesting. I'm going to let them talk about it. You don't want to hear from me. But before we dig in, I did see a lot of new names, companies attending. So I wanted to explain real quickly what AFFOA is. So our mission is to accelerate textile technology and manufacturing breakthroughs through to safeguard the nation, to advance industry, and to improve quality of life. And we're doing so in three different areas, or three different prongs, I would say, our strategies. We have a technology and manufacturing readiness advancement. So we're working with companies to be able to develop new technologies, to new processes, to be able to make things faster or easier. Lots of different areas in which we go and help in that area. We also have a domestic supply chain connectivity. So we work diligently to be able to connect companies with other companies, whether that's to build a nice robust supply chain or to connect companies that have complementary capabilities. So that way they can progress faster and be able to reach their goals to where they need it to be. And then we have our education and workforce development division, and they focus on being able to create this pipeline of people with the right skills coming out of schools to be able to go in and work in manufacturing and advanced fabrics and be able to have the skills that the companies are looking for and just be able to go and hit the road, start working right away. We work with companies as well as colleges and high schools to be able to do this. They do a lot of great work. I recommend digging deeper on that area as well. Just a tad bit more about AFFOA. So we are a 501c3 nonprofit. We were founded in 2016. And for those good at math, that's 10 years. This is our 10th anniversary year. And we are a Manufacturing USA Institute. We have 150, well, actually over 150 members across 35 states with 4 fabric discovery centers. All of our members are listed over here on the right. This is the Fabric Innovation Network. We have quite an amalgam of different industries that fall under advanced fabrics, and in manufacturing, it's pretty interesting to see who we have within there. We are headquartered here in our new location in Bedford, Massachusetts, where we have a state-of-the-art prototyping facility, and we have over 35 employees, over half of which have advanced STEM degrees. So we've got this hub of unique equipment, very skilled experts. So it's kind of a great resource for our members in the U.S. industry. And when you have unique equipment, unique experts, and we want to be able to give you access to these to be able to progress on your product development or your manufacturing project enablement there. And we've launched our 3rd version of our product accelerator for functional fabrics. And this is specifically designed to accelerate advanced textile product development and manufacturing growth for U.S. manufacturers and innovators. Really, it gives no cost access to our team and equipment, and that way to either fill in gaps in your processes, to help kind of get something over the finish line, to take a concept and move it along further on the TRL or MRL scale. And this particular version, this 3rd PAF 3.0, is really focusing more on digital engineering and manufacturing, textile manufacturing automation, manufacturing scale up, and progressing the TRL, MRL of advanced fibers and fabrics. You can learn all about this program at affoa.org/PAF. That's affoa.org/PAF. And before I move on, I do want to iterate that there are 2 really important deadlines coming up. So we have February 1st is when office hours end. And what office hours are is you have the ability to go in and book some time with our team to either review your proposal or get some answers to your questions, or really whatever you need to be able to move forward within PAF. And it's a good resource. It's not often that you get that many experts on a call with you right like that to be able to help you with your proposals. And speaking of proposals, February 15th is when pre-proposals are due, and that's part of the overall process, and it's a requirement. So please book your time with our team, and that way you'll be able to meet that deadline for the pre. So let's dig in. So a little bit of housekeeping before we jump. While the presenters are presenting, if you want to ask a question, feel free to use the chat or question button. Just type it in, and then we will have a question and answer session right after the webinar, after the presentation, actually, as part of the webinar. And I can either read those questions on your behalf, or I may ask you to unmute and ask the question. So that way you can have more of a conversation than my dull voice asking your question. So keep in mind for that. We do ask that everyone mutes unless they are speaking. I know it can sometimes accidentally unmute. You may see a message from me saying, please mute, and you'll be fine there. And last but not least, we get a lot of questions of whether the webinars will be recorded. Yes, they will. If you are a member, you'll be able to access the webinar on the member portal in the next few days. I say next few days just to cover myself in case there's a technical glitch. Odds are it'll be there tomorrow morning. So there we are with that. So today's speakers, we have three really great speakers. I'm excited to have them on the stage here, a virtual stage. I'll tell you just a little bit about them, and I apologize in advance, but I think I've got the names well, I think. So Dr. Dmitri Tsentalovich, Tsentalovich is the co-founder and chief technology officer of DexMat. He's a chemical engineer with over 15 years in CNT processing and conductor manufacturing, sorry. He's been published in over 35 CNT publications. He's been featured in Forbes 30 Under 30 while he was with Rice University. Our next speaker will be Sofia Izaguirre, who's an application specialist at DexMat. Her background is in biomedical engineering. She's helped launch DexMat Galvorn CNT fabrics with downstream processing, twisting, braiding. She's just an expert on Galvorn. It's pretty interesting to hear from her. And she now links technical advances to commercialization, driving partnerships and market adoption. And our third speaker today is Dr. Tyler Dolmetsch. He's a research and development consultant at Thaero. His background is in material science and engineering, with a focus on multifunctional materials, nanocomposites, and deployable manufacturing. He is a PI on a DARPA Phase 1 project for a plasma-activated protective fabric with active decontamination. So that's enough from me. Let's dig in. Sofia, if you'd like to start, I'm going to stop sharing if you would like to start sharing your slides. And Dmitri, you're going to be taking the stage first, I believe.
That's right. Hi, everyone. I'm Dmitri Tsentalovich, and I'm excited to talk to you today about Galvorn, a material that is highly sustainable, high performance, and based on carbon nanotubes that we're developing at Galvorn. And we'll also touch base on a couple of applications that are being developed with this material today. So go to the next slide. So we'll like to start this session off with a bit of an interactive approach. And I'd like everyone to think about what are some of the issues that current conductive textile materials present for you in your products. And so please take the time to respond to this poll question. What is the most difficult advanced textile challenge your team faces today? The potential answers are durability, meaning conductivity degrades too quickly after washing, sweating, or mechanical abrasion. Stiffness, the conductive elements are too rigid and constrain natural body movement. Weight, the cumulative mass of metal threads and their insulation layers adds a significant load. Termination in interconnects, the soft textile and rigid hardware are the greatest points of failure. Manufacturing scalability. The material is too fragile or specialized to run on industrialized standard industrial equipment. Or environmental stability. Performance spikes or drops due to extreme temperatures or high humidity field conditions. So please take a moment to answer that question, and we can move on to the next slide. So all those issues that we mentioned in the poll question are things that we think could be addressed by deploying Galvorn in these type of textile applications. Galvorn is a material that has an extraordinary combination of properties that is unmatched by any other material. Its electrical conductivity is, or electrical resistivity is 10 times lower than the best silver-coated nylon yarns, while at the same time having 17% higher thermal conductivity than copper at a tenth of the density of stainless steel, making it a very lightweight material. At the same time, Galvorn behaves just as any other cotton or textile thread and is 1,000 times more flexible than metal wiring. And coupled with all this is extremely high strength, where Galvorn is comparable in strength to materials like Kevlar. It's also highly corrosion resistant, flame resistant, cut resistant, and it's recyclable, meaning we can take Galvorn that's been used and put it back in our process and make it into Galvorn with no loss of properties. Next slide. DexMat has a highly scalable process for making Galvorn. And the way that this process works is we take raw carbon nanotubes, which come in a pelletized or powder format, and we dissolve the carbon nanotubes in a solvent. At very high concentrations, when we make a carbon nanotube solution, it forms a liquid crystalline phase, which basically means that the carbon nanotubes start to spontaneously orient and pack together with one another. And what you end up having is a polydomain liquid crystal. But when we push this liquid crystalline solution through a series of small holes that kind of looks like a shower head, and it's called a spinneret, we cause all these domains of liquid crystalline nanotubes to align in one direction. And then, and this is step 2 of the process, and get densely packed together, and we push them through a coagulating liquid bath that removes the solvent and causes the carbon nanotubes to all coalesce and lock in that highly aligned structure where they're all oriented in the same direction and densely packed. And then we wind up the fibers onto rollers at very high speeds, at which point they are now 100% carbon nanotubes with some steps to basically remove any excess solvent. And what this is known is wet fiber spinning. This is a process that is used a variation of which is used to make materials like Kevlar, rayon, and other viscose fibers. And it's been scaled to very large commercially industrial scales. So it's generally a very efficient process in order to make these type of fibers. As I mentioned, we end up getting a very densely packed fiber. So you can see in the image on the right, which is a scanning electron microscopy image that shows you the dense packing of the carbon nanotubes in that fiber. And as I mentioned earlier, we can take the fibers after they've reached end of life and put them back into our solvent in step 1 of the process and recycle them to make Galvorn again with no loss of properties. Next slide. And here, what we are showing you is just a portion of our production line that is the collection point of the fibers. We can't show you the entire machine because it is going to have some proprietary information that we can't show, but this is just showing you the speed at which we are able to collect our fibers, which is actually faster than the production speeds used for doing things like pan carbon fiber precursors. And if you go to the next slide. Since we first started making Galvorn, we've increased our production capacity by a factor of 3000x while reducing costs down to by 99.6%. And today we're still at relatively small annual production capacity of about 1/3 of a ton per year. However, because we have such a lightweight material, this actually translates to pretty significant length of conductive thread, where about 18 million meters of thread is possible to be made. That's about 150 microns in diameter from this 300 kilogram per year annual production capacity. However, our goal is to get Galvorn to be produced in large volumes and very low costs to be on par with commodity materials like copper, aluminum, and steel. And so we have an aggressive scale-up plan where just later this year, we're already going to 10x our capacity and be able to produce Galvorn at about 3 tons per year. And by the next 5 years, we anticipate building our first of a kind commercial plant, which will enable us to produce about 3,000 tons of Galvorn in a single year. And that translates to about 180 billion meters of 150 micron Galvorn thread. In addition to the thread, there's a number of other form factors that we're able to make. And to talk about that, I'm going to pass the torch off to Sofia.
Thanks, Dmitri. All right, so Dmitri just went through the process of how we make Galvorn, and so I'm going to cover the form factors that we make Galvorn in. We start with a fiber tow, which is the end product of the fiber spinning line that Dmitri described in an earlier slide. These are continuous single filaments that run parallel to each other, and they range in between 30 microns in diameter to about 50 microns in diameter. Those are the ones that we readily have available, but we can make them thinner or larger in diameter, depending on what the application calls for. And we can take these toes, these loose toes, and twist them to form yarns or twisted or braided yarns. This is about 0.5 millimeter in diameter. We can make all the way from 17 texts to hundreds of texts in yarn. And the great thing about our yarns is that they can drop into existing manufacturing processes and equipment such as sewing machines, embroidery machines, knitting machines. And although they're not as stretchy as other typical textile yarns, they can still run very efficiently on these machines. And I have 2 samples of some of these knitted meshes or fabrics. And the great thing that you can see here is that you can manipulate the physical properties of these fabrics. As you can see, this one is a lot more flexible and supple to the touch, and this one is a lot stiffer and more rigid. And we can do that. We can achieve this by either playing around with the construction of the fabric or playing around with the construction of the yarn. And we can also target any type of specifications with our yarns to reach a specific linear resistance based on what the application calls for. And lastly, we have this ribbon-like, highly aligned film. We call it film or tape. This is still very flexible and very strong and electrically conductive. It's about 10 to 20 microns in thickness, and typically we make them in 1 to 2 centimeter widths, but we can go wider or more narrower, depending, again, on what the application calls for. So I'm going to cover some of the prototypes that we've developed at DexMat. And this one was actually through a project that was sponsored by AFFOA in partnership with a company called Hexoskin. They make EKG vests and t-shirts, and they typically use these silver-coated fabrics that after multiple washes start to oxidize and you get a degradation in the EKG signal. So the goal of the project was to assess whether Galvorn-based electrodes would have comparable performance in terms of EKG signal while also have that washing durability. And by the end of the project, we were able to prove that it does indeed provide reliable EKG signal while also holding up to multiple wash cycles without a degradation in performance. This is a little demo that we made in-house. We just stitched some Galvorn yarn onto a white backing fabric and connected that to a power supply. And you can see here on the left, we're showing the resistive heating properties of the material. We were able to produce enough wattage to heat the fabric up to about 70 degrees Fahrenheit.
Looks like we may have lost Sophia for a second. I think she may have gotten booted off the internet network, so I can continue talking through the slides while she tries to join back on. So essentially, this is an application that can be used for heated jackets, car seats, etc., and requires a very small quantity of Galvorn to be able to generate the amount of heat that you would need for that application. You want to go to the next slide? I don't know if we can since Sophia's not there.
Yeah, she was
I
in
can share
control.
my screen. Sorry about the technical difficulties.
One moment, I do have a backup deck. One moment, please.
Can everyone see this one?
Yes.
Another application that is possible with Galvorn is based on the fabric form factor that Sophia demonstrated. And there's a wide range of different applications that are possible with this fabric form factor. One that customers have been pursuing is the EMI shielding and signature management. And it looks like Sophia is back, so I think I'll pass the baton back to her, but I'll finish on the signature management. Essentially, if you have a vehicle that you're trying to hide in the field and or camouflage that you're trying to have on the soldier for protecting from being able to be detected by radar. having a material that is able to shield from electromagnetic signals that is lightweight is highly important. And is there anything else, Sophia, that you want to specifically mention around the signature management?
Sorry about that. I think I lost connection for a minute, but no, I think you've covered it. Thank you for stepping in. Are you sharing right now?
I am, yeah.
Okay, just continue sharing. We'll move through the slides. Another application that our customers are testing Galvorn for is lightning strike protection. Typically, traditional aircraft is made with aluminum, and of course, aluminum is a great conductor, so it can just absorb that strike and channel the current out through an exit point. However, more modern aircraft is being built with carbon fiber reinforced polymers, and carbon fiber is a poor conductor, so you do need an additional metal layer that can absorb and mitigate that lining. And of course, metals, we know they're heavy and rigid, and so being able to replace that with a lightweight material such as Galvorn and take advantage of the great conductive, electrically and thermally conductive properties of Galvorn presents a great advantage here. And lastly, we're also working with some customers that are exploring flexible heat exchangers. And this takes advantage of Galvorn's excellent thermal properties. You are able to also take advantage of the flexibility of the material because you can make, you can get creative with the designs of the heat exchanger. You don't have to be restricted by certain designs that are not allowed by metals because they're rigid and not flexible. And so being able to conform these heat exchangers to different surfaces is a great advantage that Galvorn presents. Next slide. Another application that we're developing with one of our customers, they're called Tokai Rika. They're a Japanese auto supplier, and they're using Galvorn to make flexible thermoelectric generators. And the idea here is to turn waste heat that's generated in any type of process and turn that heat into electricity. And for example, the example here is this cow that has a tracking device on it. This tracking device is typically powered by batteries. And if you have a flexible generator in there that just turns the heat that's generated by the cow and turns that into electricity, you can have a tracker that is continuously monitoring the location of the cow without having to worry about switching out batteries or having to worry about an external power source. So again, the properties that Galvorn has that enable this application here are its flexibility and its great electrical and thermal properties. And this wasn't an application that was on our radar for DexMat, but it proved to be very interesting. And another interesting application that was not on our radar is something that Tyler is going to speak on, the work that Thaero is doing on using Galvorn for protective gear for biological and chemical agents. So I'll pass it on to you, Tyler.
Awesome. Thank you, Sophia. So today I want to talk on behalf of Thaero and our DARPA Phase 1 STTR project, where we titled it AMPS, or Active Materials for Protection Sustainment. And I'll talk a little bit about the project and then how we were able to partner with DexMat here to actually make this project a success. So if we can go to the next slide. So Thaero was founded back in 2023, basically identifying the need that in today's environment, we need new materials that could be more multifunctional, that are able to withstand higher temperature environments or actually be able to sense the environment around it. So the first thing we were starting to commercialize was radiation-resistant metal matrix composites, and these are enabled by adding in different types of nanoparticles into your traditional metal matrix systems like aluminums or steels. And also working with those nanomaterials, we realized that we can solve other challenges, which actually led us into this DARPA project for basically decontaminating against chemical and biological agents to improve current CBRN suits that have had known challenges with not being able to protect against all of the environmental factors all at once, such as radiation, the chemical agents, biological agents, and generally they're very hot suits, so people can only wear them for about 20 minutes before they have to take them off or sit down so that they can recover from kind of the heat exposure. And also they're not reusable. So you wear them once, and whether or not you're involved with some sort of chemical, biological, radiation agent, you have to dispose of it. So the cost can add up very quickly. So yeah, that was kind of a brief intro into the challenge that we're doing here at Thaero. And if we want to move to the next slide, I'll talk a little bit more about kind of our key challenges that we wanted to address. So one is we wanted to make this modular. So it is a layered composite. And really the one that I'm going to be talking about today is the outer layer, which is our active plasma fabric. So we're trying to address with that, overcoming passive barrier limitations in the current PPE suits. So as I mentioned before, generally you want to just keep the chemical or biological agent out. And that's been, the entire concept for traditional suits, but we wanted to take a more active approach and allow the warfighter or equipment to go into the environment and actually be able to actively decontaminate against these agents. We also wanted to enhance the multifunctionality of these suits. So generally you'll have suits for the different environments, but sometimes you don't know what you're walking into. So we wanted to make sure that the next generation of suits are able to decontaminate or protect the warfighter from all of these different problems. And we wanted to make sure that while we do this, we don't want to add too much weight. We want to make sure that they're durable. Again, we're going for reusability. So this needs to be something that can go through multiple cycles, which is also going to eventually reduce the overall cost of the suit. If we go to the next slide. So for the outside layer, I mentioned this plasma fabric. Basically what we're trying to do is we're able to run an electric current through the outer fabric system, and we're able to create basically a dielectric breakdown barrier. And this comes as this kind of glowing purple plasma that you see here. Now it is a cold plasma relatively, so the overall composite itself never really goes above 100 degrees Celsius. And by doing this at different voltages or different resonant frequencies, we're able to kind of tune the plasma fabric to give enough power to be able to actively decontaminate against known chemical and biological agents. So this here is basically our kind of version 1, very basic. The base metal here is copper, but as we know, copper very heavy. It's going to oxidize over time, even at these kind of lower temperatures. And the basic kind of parallel layer here is not very flexible. So if we want to go to the next slide, please. So to actually do this for testing against chemical and biological agents, they have to be in kind of this reduced form factor. So it's about 2 inches in diameter. We'll call it fabric samples here. And you can see we're testing these at various voltages, frequencies, the dielectric thickness itself. In the video there, I don't know if it'll keep playing or not, but basically just real time, it's glowing purple, which is really cool to see. And it's fun to play around with. But if you're in an active war zone, you don't really want to be glowing giant purple. And the sound is off here, but it also makes kind of a high-pitched noise. So they'd be able to see you, hear you, and that wasn't great as well. So along with the stiffness of the fabric, prone to oxidation, hard to integrate with traditional layers, and this glowing and sound that comes with it, we wanted to move to something that had higher strength, was more lightweight, more flexible, kind of solved a lot of these challenges. And that's actually what led us to DexMat in the first place. So I had seen their, different Galvorn videos on LinkedIn. That was how we initially found them. And I thought it was a great technology. And I was kind of dying to integrate it into some of our different technologies that we've been working on over the years. And this was definitely a great opportunity for us to work together. So if we go to the next slide. So working with them, we were able to transition this plasma fabric not only to something that was not just parallel or like kind of a sheet form. We were able to make this coaxial design. So we had this design kind of in our heads, but we just didn't know exactly how we were going to integrate it. But being able to work with them and introduce the Galvorn, which is not only flexible, but it's actually conductive, we're able to basically make an activated plasma fiber with this technology. So by introducing Galvorn, we were able to make everything lightweight. It had a much higher strength than the copper. It's also cut resistant. and high temperature resistant. So being able to put this on the outside of our fabric layers was able to protect the warfighter from other threats, basically from like that cut resistance. I think you guys have looked at some, bullet resistance. I'm not sure how far that's gone yet, but eventually that would be something great to integrate as well. Being able to make our suit as high strength as possible while being able to actively decontaminate against this. So we were able to make these 40-foot spools of this form factor, and that was able to transition us into the next slide where we can actually see the fabric itself. So the very center is what the form factor looks like right now. So we were able to take that coaxial fiber and basically kind of wind it up into a spool. And just as a basic feasibility, we were using lamination to put all of our different layers together. So the outside is this cold plasma fabric. Underneath that is our radiation shielding layer. And then below that is some EMI shielding as well. And then the final layer, which is closest to the warfighter, is for thermal regulation. And that's using a phase change composite. So basically, whether it's hot or cold, we're able to keep the temperature regulation. So this was in that 2-inch diameter form factor, and that was allowing us to send off samples both to Battelle, which was going to do the chemical and biological testing, as well as to NASA, where they were going to do the neutron radiation shielding. So we've had some very promising results from both of them. We're waiting to get the final results now. Basically, we're kind of in the last month of our contract with DARPA, so we'll be writing up that final report. But based on everything that we've learned so far, and on the right-hand side here, we can see the portable power supply that we had to create for this. So really the next stage is being able to transition this not to only some kind of small R&D project, but we actually want to take this larger and make these like more flexible knitted swatches like Sofia had shown before. We want to be able to transition this into decontamination bags or decontamination blankets. And then eventually going towards kind of a more full-fledged suit that the warfighter could use. But yeah, I'd say the main thing out of this was without being able to have some sort of lightweight, high conductive fiber, we would never have been able to actually make this into something that could be transitioned into more of a suit type layer for the warfighter, because no one wants to walk around with a giant copper suit. So we're definitely thankful to work with DexMat on this, and I'm looking forward to working together in the future to actually optimize this and make it better. So hopefully the next time we give this webinar, I'll be able to wear some sort of suit and you'll see me, maybe glowing purple or, solving all of the needs that we want. Yeah, with that, I'll turn it back over to the DexMat team.
And just to summarize, thank you, Tyler. What Galvorn is a material that has an unparalleled combination of unique properties, and it has a lot of potential applications. We just gave you a taste of some of the things that are possible. However, you might have something completely different in mind. And so if you're interested in getting some Galvorn material, please, you're welcome to buy a small sample directly from our website, or better yet, reach out directly to myself or Sofia, and we can help you get the right Galvorn for your application. Thank you very much, and I'll turn it back over to Josh for the question and answer session.
Hi, I did get a couple come in while you were presenting. And I ask anybody in the crowd there in the audience, if you'd like to ask a question, feel free to just raise your hand or submit it via the Q&A or chat. Be more than happy to help get you in that conversation. The first one that came in here, you mentioned it's super strong. Will we have to tune our machinery to work with Galvorn?
Sofia, would you like to take that question?
Yeah, I can answer that. Thanks, Josh. So the material is very strong, but we do have 2 grades of material. We have one that is high conductivity, high strength, and we have that is specifically optimized for conductivity and to run in textile equipment. So it's not as strong as our high strength grade, so it shouldn't damage equipment. And also, there is some fine tuning that you can do on the equipment, like working with the tension, because our yarns are stiffer than certain textiles. They're not as stretchy. So there is some fine tuning that you have to do with the tensioning of the machine. But once you get that tension right and you get it going, it should be a smooth process.
Great. I've got a question here from Chrissy Glover. Chrissy, would you like to unmute and ask? If that's a no, that's fine. I'll ask for you then. Can Galvorn be soldered?
Sophia, you want to take that one as well?
Yes. So yes and no. It can't be soldered. It cannot be soldered with traditional solder. There are some carbon-based solders that could work with our carbon-based material, but also there's other termination alternatives such as crimping, and it's also a textile, so you can tie a knot. That works well. But we also, you're able to electroplate the Galvorn ends with another metal such as copper or nickel or silver, and then you can then solder and wet that electroplated part of the material. So it's a little bit of a workaround, but there is a solution to it.
Great. I've got a question here saying, are you looking for weave partners?
I'll take that one. Yes, definitely. We are looking for weave partners. In fact, we have some in-house capability for assembling fabrics, but they tend to be small swatches. And we've actually had a couple of companies that have requested larger area fabrics, which we want to partner with companies that have those large pieces of equipment rather than trying to bring all that in-house. So definitely, the answer is yes.
Great. I also have another question from the group. What's the smallest feasible fiber diameter?
I'll take that one as well. So we have made fibers for customers as small as about 5 microns. This is very difficult to do just because handling such small diameter fibers is very difficult. So if you have a single filament fiber, then just the amount of force it takes to wind it from one roll to another can break the fiber. But and potentially we could make them even smaller if you were to ask for a multi-filament tow or a yarn made up of really tiny fibers. We could go smaller, but so far 5 microns has been the smallest diameter that we've practically been able to make and then handle and post process.
Great. Let's see. Circuits. Carlos, would you like to unmute and ask your question? All right, I think maybe there might be some unmuting issues there. So a follow. Oh. If using the fibers to interconnect circuits instead of copper wires, is the insulation for the fibers, if not, do they short if in contact with each other?
Sophia, you want to take that one?
Yes, so you can insulate the fibers. We've actually we've run our yarns, our twisted yarns through, and actually single filament fibers as well, through extrusion processes where the insulation is being applied via extrusion process. So it is possible to insulate them. We can also apply an overbraid insulating material such as, nylon or Kevlar or any material that would be preferred. So yes, they can be insulated and they will short in contact with each other. So it's important to insulate them.
However, I will also like to add to that the conductivity of Galvorn fibers is anisotropic, which means that the conductivity is higher in the axial or alignment direction than it is in the radial direction. So actually, we've done some tests where, especially when we were just passing a low amount of current through the fibers, even when they come in contact, that doesn't always short the product. And so you can get away with it a little bit, but I think if you're running, higher currents or you have them in very close contact, then they will likely short unless they're insulated.
Okay. Here's another one I received. I see it's cut resistant. How would we integrate it into our textile equipment if we aren't able to cut it during large volume runs?
Sophia, you want to take that one?
That's a great question. The cut resistance is great for some applications and not so great for others. But if the yarn is being held under tension and you're using a sharp blade, you should be able to cut through it. It's just a matter of switching out your blades so that they're always fresh and nicely sharp. And also, it should a laser cutter should cut through it very neatly as well.
Great. Let's see, I've got one collaboration inquiry. I'll send that privately. And unless we have any further questions from the audience, raise your hand real quick if you, oh, wait a sec, we just did get one. Okay, well,
Hi, can you hear me?
yes.
Oh, hi. Okay, it worked. Yeah, I was wondering about the thermal resistance of Galvorn. Like, what temperatures can it withstand before degrading?
I can take that one. So the answer is it depends on the environmental conditions. So in air, if you expose it to temperatures above about 350 Celsius, then you'll start to have the Galvorn start to oxidate, and that's due to the presence of oxygen. If you have the Galvorn in an inert environment such as vacuum or nitrogen or argon, then it can go up to over 1,000 degrees Celsius without degrading.
Great.
Great, thank you.
Carlos, I have a.
Can you hear me now? Thank you. Following up on the interconnection, so you mentioned that for termination, Sofia mentioned that you can tie a knot, to interconnect some things. But I also hear that there is an isotropic conductivity situation. So wouldn't it be then better to terminate with like a point, if you will, at the fiber axis rather than with a knot? And would that be significantly different in performance?
So I think that as long as you're in close enough contact with the presumably metal structure that you're trying to, or metal interconnect that you're trying to connect it to, then most of the current will just go through the kind of axial direction of the fiber anyways. But it's important to either have a crimp, or if you tie a knot, that you tie it very tightly. And this is still an area of ongoing research. We haven't, built every type of cable possible with Galvorn, and at some point there may need to be specific terminations for certain types of connections that are required. But so far, what we found is for running, relatively small currents, we haven't made, thick power cables with this material yet, that a crimp connection or a knot, or in some cases, as Sophia mentioned, a soldered connection that's based on initially plating some metal and connecting to termination has worked very well.
Gotcha. And so for on the insulation side of things, is it possible to insulate even your smallest fiber? Like I know that there's some limits in like sizes and workability with it. So I'm just trying to understand the limit and how small can a fiber be that is insulated.
It's definitely possible to insulate very small fibers. I think we've done fibers. Our typical fiber size is about 20 microns, and we've had a partner that's been able to insulate those. And this partner has capabilities of applying insulation to even thinner material. It's just at some point you need super precise control of your winding, and so the smaller you get in diameter, the smaller your break force gets. And as long as you are able to roll process it, then you can insulate it. Of course, potentially you could insulate a very short segment, but generally for most textile applications, you're going to want to do a roll-to-roll insulation process. So I'm not sure if how easy it is to do a 5 micron insulation, but it's probably possible.
And what is the thickness typically of the insulation? Like, is there? I guess this may be too into the weeds, but like kind of like temperature resistance of the insulation itself, you know, what material it is, how thick, and so on?
That varies based on the application, right? So in some
Right.
applications, you want as thin a layer as possible, and in some applications, you want a very thick insulation.
Right.
We'd be happy to, you know, if you have a specific application in mind, to kind of send you what's possible for the, you know, fiber size that you're looking for.
Sounds good. We'll be in touch. Thank you.
Great. I'm going to squeeze in one last question. I thank everyone for staying a little over time. This question is, can you speak a little bit about Galvorn's resistance, UV resistance, sorry, cryogenic extreme cold resistance? Can you speak a little about that?
Yes, I can give you a bit of a flavor of the testing that we've done. We actually have some testing ongoing with the Mississippi Polymer Institute, where they're doing accelerated aging tests by studying the effects of different humidity and temperature conditions on Galvorn. We do know that Galvorn has been shelf stable for over 10 years from, you know, the initial Galvorn materials that were being produced back in about 2015, and they have not had any degradation in conductivity or strength. However, we have not done a lot of UV exposure experiments, and that's one of the things that is going to be evaluated with some of this accelerated aging testing that we're doing. We do not think that there is any degradation due to UV exposure from kind of short-term exposure to UV that we've had. Long-term has not been fully tested yet, but unlike materials like Spectra, we don't think that this, or PBO fiber, that this is going to be an issue with the Galvorn material because it's carbon-based.
I would
Great.
say also, whoever asked that question, we will be publishing our accelerated aging results on our website, as well as our social media like LinkedIn. So stay in tune if you would like to learn more.
Great. Well, this has been an outstanding presentation. Thank you so much. The team, you survived one of the biggest worries about doing a live webinar, and you did it spectacularly. Thank you. I'd like to thank everyone who's attended, and please note that you have the speaker's contact information on the page. So if you'd like to be able to reach out to them, I do recommend you do so. And if you're not following them on LinkedIn, please do so right away. That way you can get everything up to date as soon as it comes out. So with that, thank you to everyone, and you have a great rest of the day.